Okay, so today's lesson is about rational functions. Now, a rational function is pretty much, I like to think of it as a fraction function. It's a function that has a function on the numerator and also a function on the denominator. So it's pretty much two functions being divided by each other. Anytime I hear the word rational, I think of the word fraction. So I can always tell if a function is a rational function just by telling, is it a fraction or not? So for example, I've given us 3 examples. Each of these are rational functions. They're fraction functions because the numerator is a function, x squared minus 4. That's a quadratic function. The denominator is also a function, x squared plus x plus 1. That's a quadratic function. So we have 2 functions being divided by each other. Therefore, it's a rational function. Same thing for the second example. We have a cubic function on the numerator, x to the 3rd power, and then we have a quadratic function on the denominator, x squared minus 4. So we have 2 functions being divided by each other, and therefore it's a rational function. And the last one, once again, it's a fraction function because we have a 3x squared quadratic function on the numerator and a x to the 4th power, that's a 4th power function on the denominator. So these are just some examples of rational functions. You can always tell pretty easily if a function is rational just by looking at its equation and saying, is it a fraction or not? Okay. Now, not necessarily a fraction because we could have, let's say, y equals 3/4 x. That's not a rational function. I mean, it has a fraction, but there needs to be x variables on the numerator and denominator. Or there needs to be at least x variables on the denominator. And so in this case, not necessarily just a fraction, but a function on the top and bottom of the fraction. Just erase that. It's not an example. Okay. All right. Now, the common distinction about rational functions from other functions, if we're looking at their graphs, it has a pretty clear distinction in their graph from other functions that we've learned about, is something called asymptotes. Okay. Rational functions have asymptotes. There's 3 different type of asymptotes that a rational function can have: vertical, horizontal, or oblique. And asymptotes are really kind of just basically boundary lines. The first thing I'm going to do is I'm going to go ahead and write down the definitions of each of these 3, and then we're going to go ahead and do some examples on how to find each of these different types of asymptotes from a rational function. So the first type of asymptote that a rational function can have is something called a vertical asymptote. And all a vertical asymptote is, it's pretty much just a vertical, that means up and down, a vertical boundary line that a function approaches, it gets really, really close to, but it doesn't actually ever intersect. So it's a vertical boundary line that a function approaches but never crosses or intersects. Okay, and we'll do some examples on what that looks like in just a bit. But it's pretty much some imaginary boundary line, vertical. The next definition is horizontal asymptote. Very similar. It is also kind of a boundary line of some sort, except a horizontal asymptote is a horizontal, meaning side to side, horizontal, left and right, a horizontal line that a function approaches. It gets really, really close to as x gets larger or smaller. Okay. And you can ask for, I'll go ahead and write that in because I think the textbook definition has it. As x gets larger, meaning as x goes all the way to infinity, or as x gets smaller, meaning all the way back to negative infinity. Okay. And then the last type of asymptote is the oblique asymptote. Now this one isn't as common. I think we'll just do maybe one example on it. But an oblique asymptote, another way to say oblique, I've also heard of a slant asymptote. So they mean the same thing. You might just hear slant or you might hear oblique, but pretty much means it's a diagonal or linear boundary line that a function approaches, it gets really close to, but it doesn't ever intersect. Never crosses. Diagonal meaning, something like that, or it could be in the opposite diagonal direction. So those are the three types of asymptotes a rational function can have. I have the textbook definition of vertical asymptote and horizontal asymptote. If you want to read through that, it's a little wordy and confusing. These are my informal definitions that I came up with, but you can also refer to these if you want to use these definitions as well. So we have three definitions, three different vocabulary words, and I've given us 4 different graphs down here. Just real quick, I wanted to identify what type of asymptotes these graphs have. If you look at the graph A, our function, well, I'll go ahead and darken it in case you can't see it. It looks like this. There's kind of like a vertical break, and they've even used a dotted line to kind of help us see. There's this vertical, it's an imaginary vertical line that the graph doesn't ever intersect. It gets really close to, it's kind of flattening out as it gets close to it. That's called a vertical asymptote. So part A, this would have a vertical asymptote because it's an up and down line. Same thing for part B. This graph was going kind of in this direction and also going in this direction down here. And then there's this vertical boundary line. They kind of drew it for us. That the graph doesn't ever intersect. It kind of just gets really close to it. It kind of starts flattening out as it gets close to it. This is an example of a vertical asymptote. So this is what it would look like. Most rational functions are going to have breaks in them. See how it was kind of a break. The graph was here and then it kind of broke and then it continued. The graph was here, it broke, and then it continued somewhere else. Rational functions tend to look like that. Part C, we have this graph, and I'll go ahead and darken it for you. And notice as I continue tracing out this graph, it kind of starts to flatten out. The graph kind of starts to flatten out into kind of just like a horizontal flat line. So this horizontal dashed line that they've already kind of marked for us, this is called a horizontal asymptote because it's this horizontal boundary line, in which case the graph starts to flatten out at. And then same thing for this last graph. If we kind of trace this graph, as x goes to negative infinity, meaning as the graph goes backwards, the graph kind of flattens out, and it flattens out at this y value. At this y value is where it starts to flatten out. So this would also be called a horizontal asymptote. So each of these pink dashed lines that I've kind of marked, those are all asymptotes. So those are what vertical and horizontal asymptotes look like. Just to kind of extend on that, for our first example, I've given us 4 graphs, and I want us to actually state what are the vertical and horizontal asymptotes for each one. So starting with graph A, and I've kind of already marked out the dashed vertical or the asymptote for you. I kind of said the answer. But for graph A, notice the graph has a break right here. And so this is called a vertical asymptote because it's up and down. So I'll go ahead and say it has a vertical asymptote. And I want to write the actual equation. Now since this is a vertical line, vertical lines, the equation would just be x equals, now the x value, which is -1, would be our vertical asymptote. So there's a vertical asymptote at x equals -1. For part B, there's actually 2 asymptotes here. There is a vertical one. This is a vertical line that the graph doesn't ever intersect. It just gets really close to. See how the graph kind of gets close over here and it gets close there, but it doesn't ever cross the other side. So this would be a vertical asymptote. And since it's a vertical line, the equation of any vertical line is always x equals, and then the x value is 1, 2. So the vertical asymptote is at x equals 2. That is not the only asymptote that this graph has, though. There is also a horizontal asymptote right here. And this horizontal asymptote is side to side. And so the equation of a horizontal line is just y equals And then the y value at this horizontal line is just 1. So y equals 1. And that's it. Okay. I'm running out of space here. All right, part C, same thing. We have actually 3 different asymptotes. A graph can always have more than one vertical asymptote. In this case, there is 2 vertical asymptotes. There's a vertical asymptote right here and also right here. So there are 2 vertical asymptotes, and I'm going to go ahead and write down each one. The first one is at x is equal to positive 2, and also at the x value negative 2. And that's what you would write. This graph also has a horizontal asymptote right here, and that horizontal asymptote is at the y value 1. So you would just say that the graph has a horizontal asymptote at y equals positive 1. Okay. All right. And then last one, part D. Now this line, this asymptote, this dotted line, is not vertical or horizontal, but it's clearly some sort of boundary line. This is being an example of an oblique or slant asymptote. So it does have an oblique or slant asymptote. The equation, I'll go ahead and put slant. The equation of this line, we're not actually sure. We could actually try to figure it out by getting 2 points and making an equation of it. But I won't worry about that too much right now. I'll just go ahead and say it has an oblique slant asymptote. And the equation of the line would be probably y equals, well, the slope is up 2 over 1, so 2 over 1, x plus the y-intercept is 0, so plus 0. So we can go ahead and write that, but just know that this graph has an oblique or slant asymptote. If you don't do the second part, that is fine. You can leave it as is. You don't even have to write plus 0, but that's fine. Because this is a linear function, so the way you write linear functions is you start with the slope, which is up 2 units over 1. I just picked 2 points, and I calculated rise over 1. And the y-intercept is 0, so plus 0. There we go. Okay. All right, so we've been given graphs, and we've just been told to identify what are the vertical or horizontal or oblique asymptotes just by looking at the graph. The next part of this lesson involves us identifying vertical asymptotes from just given the equation. So let's say we don't have a graph to look at and kind of say, okay, what's the vertical or what's the dashed line? Let's say we're just given the equation, the function, and we're told to find the vertical asymptote. So that's what we're going to start with first. We're given 2 examples, and we are asked to find the vertical asymptotes of the graph, if there's any. So I'll go ahead and start with this first example. Now the first example is a rational function because it's a fraction function. It has a function on the numerator and denominator. And vertical asymptotes are found the same way. The key is the denominator. Okay. Now the first thing I want to kind of flash back to, I'm going to just write on a scratch paper. Now, like you saw above, there's these vertical breaks that occur sometimes, and you might be wondering, why do those happen? Why is the graph kind of just breaking up vertically sometimes? Why does that occur? Well, thinking about fractions, and I'm just kind of making a note out to the side, what is 3 divided by 0? Well, and you might be thinking it's 0, but if I show you, and no matter what calculator you have, you should get some sort of error, or it says can't divide by 0. Okay, maybe you just didn't like that combination. What about 100 divided by 0? Well, 100 divided by 0 is also, it gives me an error. It won't even calculate it. Okay. Now the problem with this is we cannot divide by 0. You can try asking Siri what is 100 divided by 0, and she'll give you a funny answer. But the key word is that you can't ever divide by 0. You can divide 0 by other things. Like I could have 0 on the numerator, and that would be okay. 0 divided by 3 gives me an answer. 0 divided by 100, because 0 divided by any number is 0. But if you try to divide by 0, that's when we get an error. We can't divide by 0. Mathematically, there's no number assigned to that. It doesn't make sense logically. I like to think of this little visual. This is okay to have 0 on the top, and this is not okay to have 0 on the bottom. This is okay, and this is a big no-no. So that's how I kind of remember it's okay to have 0 on the numerator, but you can never divide by 0. It doesn't make sense. There's no logical mathematical explanation or value that we can give that type of question. It's like saying if you have 3 cookies and you want to divide them among 0 friends, how many cookies does each person get? Well, there's no people. There's 0 people to give the cookies to, so you can't really actually solve that problem. And that's exactly why vertical asymptotes occur, is because you're given some function and you're trying to divide by 0 at certain points, and it just doesn't make sense, and so the graph kind of looks funky and creates these breaks, these vertical breaks in the graph. And so that's kind of a short, quick explanation of why vertical asymptotes happen. But the way that we find vertical asymptotes of any rational function is just by looking at the denominator. And the only time a vertical asymptote, meaning a break in the graph, is going to occur is whenever this function is trying to divide by 0. So what x value can I plug into this function that'll give me a denominator that is equal to 0? Now some of you might already know, oh, it's the number 1. But if you're not sure, all you have to do is take this denominator and set it equal to 0 and just solve for x. So x minus 1 equals to 0. I'm going to add 1 to both sides. Minus 1 plus 1, those cancel out. And I'm left with x equals 0 plus 1, that's 1. So I know that my vertical asymptote is at x equals 1. And there's our vertical asymptote. Now again, the reason why this answer is 1 is because what this is saying is if you can plug in any number you want for x to this function and you'll get some sort of output value. But if you ever try to plug in the number 1 for x, you will get a y value of, well, 1 plus 3 is 4, divided by 1 minus 1 is 0. You'll get 4 divided by 0, which again, like we said earlier, you can't divide by 0. So if we try plugging in the number 1 for 0, you'll get a big error. It won't make any sense, and that's why a graph will have some sort of break looking like this, or maybe one like this, or part C in the graph. Okay. Now you might be wondering, what about the numerator? Do we have to look at when the numerator is equal to 0? No, you only care about when is the denominator equal to 0. It's okay to have 0 on the numerator. It's just not okay to have 0 on the denominator. Yeah, it's okay to have 0 on the numerator, just not okay on the denominator. So that would be our vertical asymptote. And you could even graph this onto your graphing calculator. I'll go ahead and see if I can type this in. F of x equals x plus 3 divided by x minus 1. And you will see that the graph should have a vertical asymptote at x equals 1, which you will see that is true. X equals 1 is right here, and it has a break in the graph. Okay. Now this second part, it says also figure out what is the domain of the function. Now remember, domain just means what x values can we plug into this function. Are there any exceptions that won't work or will give us errors? We've kind of done most of the math already. Domain is, I always start every domain with all real numbers, or some people like to use the fancy R if you want to use this symbol. All real numbers except what can x not equal? What x value, if I try to plug into this, will give me some sort of error? Well, the x value that I would plug in is 1, and that'll give me an error. So I would say all real numbers except for 1. Or you could also just write x cannot equal 1. Okay. These two answers really go hand in hand. They look very similar, and there's questions on your MyMathLab homework, so just make sure you distinguish between the two. The vertical asymptote is saying where is the break on the graph happening? It's happening at x equals 1. And the domain is just asking you what can x not be equal to? Well, it can't be equal to 1 because that's where the break is going to happen. Okay. And there's our answer. Alright, same thing for the next one, part B. We want to figure out what are the vertical asymptotes. Where will this graph have vertical breaks? Well, the only time that happens is when the denominator is equal to 0. Because if there's a denominator of 0, then you know there's going to be errors, there's going to be vertical breaks, the graph's going to kind of break apart. So you might already know what x value I can plug into this denominator to make the whole thing equal to 0, but if not, you can set it equal to 0. X squared minus 4 equals to 0. And you can solve for x. I'm going to go ahead and just start by adding 4 to both sides. Minus 4 plus 4, those cancel. And I'm left with x squared equals 0 plus 4 is 4. And then in order to get rid of that square, what is the inverse or opposite of square? Well, it's square root. Square root and square cancel. Cross them out. And you're just left with an x value equals the square root of 4 is positive or negative 2. Because 2 squared is 4, but negative 2 squared is also 4. So you have two answers. You have two vertical asymptotes, and that's okay. And there's our answer. X equals 2 and also x equals negative. So you can write it separate, or you can just write a plus or minus symbol. Okay. The second part says also list what the domain is. Now the domain is pretty much all real numbers. Just means you can plug in any number you want. We're assuming any number will work if you want to plug in for x to this function, except what numbers can we not plug in? Well, we can't plug in 2 or negative 2, because if we try to, it's going to give us a denominator of 0. So you could just write all numbers except, you could just put where x is not equal to 2 and where x is not equal to negative 2. You could also just write it out if you wanted to write it in words, but I'll write it like this because I think this is how your homework also asks you to type it in. Okay. So these are very similar, just careful on making sure you understand what each of these mean so that you don't confuse them with the other. Okay. All right. All right, two more examples on vertical asymptotes, and then we'll move on to the next type of asymptote. All right, example number 3, once again, just find the vertical asymptotes of each graph and also list the domain of each function. Okay, so that's exactly what I'm going to do. For part A, I'm just trying to figure out when will this function have a break vertically. Okay. Vertical asymptote. Now the only time that occurs is whenever the denominator is equal to 0. Before I do that though, I just want to rewrite this problem in factored form. X squared minus 4, that's a quadratic. You can factor it, and we've learned about how to factor. You can factor it as x plus 2 times x minus 2. Okay, it's the same thing. If you want to FOIL this out, you will end up with x squared minus 4. Okay, and the denominator is still x minus 2. Now the reason I did that is because, yes, normally we would say the vertical asymptote is whenever x minus 2 is equal to 0, we would solve for x and we would get 2. However, if you just look at this function and if you factor it, you can actually see that x minus 2 will cancel out with x minus 2. So when this happens, this doesn't happen often, but when this happens, that means there is no vertical asymptotes. Because by cancellation, there's now there's no denominator so that you have to worry about setting equal to 0. When this happens, this is actually called, and I think this is a little bit of an extension, this is called a hole. It just means like it can be removed. So there is a hole at x equals 2, because if I plug in 2 for x, it'll give me a value of 0. So I can cancel those out, that's what you would say. But technically there is no vertical asymptote because you can cancel out with the numerator. You can simplify this function before having to even look at the denominator. Okay? We didn't do that on the previous problems because, well, there was nothing to factor. X plus 3 is not a quadratic, so you didn't need a factor. X was not a quadratic, so you didn't need to factor the numerator. I mean, you couldn't. However, this one was a quadratic on the numerator, so I knew that I could probably factor that. Okay. That's okay. So the domain, let's say the domain is pretty much all real numbers, which just means you can plug in any number for x, except for 2, because it won't actually have a value at 2. There you go. Okay. And there you go. All right. Okay, next one, part B. It says find the vertical asymptote. So again, we're going to go ahead and figure out what x value can I plug into this denominator that'll give me an entire denominator equal to 0. Now I notice that this is a quadratic, not just on the denominator, but also on the numerator. So I would actually first factor, just like I did over here. I'm going to factor. Anytime you see quadratics, generally you want to factor. On the numerator, x squared minus 9, you have to think of the difference of squares, or you can think of what two numbers add up to 0, since there's no middle 0 x term, and multiply to negative 9. And that would be negative 3 and positive 3. Okay. On the denominator, the way we would factor is what two numbers add up to 4, but multiply to negative 21. If you're not sure, you can make a little t-tree like we did for negative 21 and list all the things that multiply to negative 21. Negative 1 times 21, negative 3 times 7. You could also do 3 times negative 7. But you'll see that the only pair that adds up to 4 is negative 3 and 7. So I'm going to go ahead and factor this as x minus 3 and x plus 7. Okay. So what I've done is I haven't changed the value of this function. I just rewrote it. I factored the numerator. I factored the denominator. If you wanted to check, you could always FOIL out the numerator and you'll get x squared minus 9. You could FOIL out the denominator or use the box method and you'll get x squared plus 4x minus 21. So we're just rewriting it before we do anything. And the reason why we did this is because now you're going to see that there is a x minus 3 factor on the numerator and an x minus 3 factor on the denominator. So those will cancel out because anything divided by itself is just 1. Whenever you have these two factors that cancel out, that's actually called a whole. A whole. So there is a whole at the x value of 3. Okay. But as far as vertical asymptotes go, since we canceled these two out, the only denominator that we have left, we still have an x plus 7 denominator left. So I have to look at just my function that I have left. What x value can I plug into this denominator that'll make this equal to 0? Well, just take what your denominator is, set it equal to 0, and solve for x. So I'm going to subtract 7 from both sides. 7 minus 7, those cancel out. And x equals 0 minus 7 is negative 7. So that would be my vertical asymptote. That's where there's going to be a break in the graph. Okay. And then the last part, it does say to figure out what the domain is. The domain is just pretty much saying what numbers, what values of x can we not plug into this function. What x values is going to give us some sort of error or undefined value. Well, we always assume it's just all real numbers. That's just assuming that we can plug in any number we want for x, except for negative 7. So I'll just put x cannot be negative 7 because that's where there's going to be a vertical asymptote. And also at 3, because if we tried plugging in 3, you would get a denominator of 0. So you would just write, and x can also not be equal to 3. And there's our domain. And I didn't bubble it over here, so I'll do that. Okay. And there's our answer. Alright, so that wraps up vertical asymptotes, and that's how you would find the vertical asymptote of any rational function. Just look at the denominator and see what's going to make that denominator equal to 0. Okay. The next part of this lesson is horizontal asymptotes. So this last part, we were given a couple of examples, and now we're asked to find how do we find the horizontal asymptotes. Remember, horizontal asymptotes are just horizontal lines the graph approaches horizontally. So there's actually, I included a little cheat sheet, and this is important, so you might want to get this down. There is a pretty much this little cheat sheet that you can use to figure out what is the horizontal asymptote going to be. It's all about the degrees, meaning the exponents, the highest exponents of the numerator and the denominator. So just by identifying what the degree of the numerator is, what the degree of the numerator and denominator is, you can pretty much just refer to this chart, and it'll tell you what your horizontal asymptote is. So I'll go ahead and do an example first, and then we'll refer to this. So let's look at example number 4. It says find the horizontal asymptote, if there's any, there might not be any, of this function. Well, the first thing I want us to do is I want us to figure out what is the degree of the numerator. Remember, degree just means the highest exponent of x. If you look at the numerator, we have x squared minus x plus 2. The highest exponent is a 2, a second power. So the degree is 2. Now let's look at the denominator and identify what's the degree of the denominator, which means the highest exponent of x, which is also x to the second power. So the degree is also 2. These two numbers are the same. The degrees are equal. See how they're equal? They are both 2. So according to my reference chart, if the degrees are equal, that's this first case, then the horizontal asymptote will simply be the ratio of the leading coefficients. So the horizontal asymptote, remember, horizontal lines are always just y equals the ratio of the leading coefficients. Now what does that mean? Well, that just means look at the leading coefficients. That's the coefficient in front of the degree, in front of the highest exponent, which would be 8 and 4. 8 and 4. So my horizontal asymptote is just 8 divided by 4. You just take two coefficients and you divide them by each other. So 8 divided by 4 is 2, and there's our horizontal asymptote. Y equals 2. And here's your answer. Okay. Now there's other 3 cases which we'll kind of be referring to, but you just have to figure out which of these 4 different scenarios is your rational function falling under, and that's what your horizontal asymptote will be. Okay. All right, next example, I'm going to try to leave this reference chart up at the top so we can refer to it. Example number 5, it says find the horizontal asymptote, if any. Well, the way that we find horizontal asymptotes is we start by figuring out what's the degree of the numerator, which means what's the highest exponent of x, which in our case would be a 3. And then we identify what's the degree of the denominator, which is just the highest exponent of x on the denominator, which would be x to the 5th power, because there's x to the 4th, but 5 is bigger, so it would be 5. Now in this case, the numerator has a higher degree. So if I look at our 4 cases, the degrees are equal, no. The degree of the denominator is bigger, no. The degree of the numerator is bigger. Actually that one is right, my bad. The degree of the denominator, which is 5, is bigger. So in our case, this would be the second scenario. And it tells you that the horizontal asymptote is just going to be y equals 0. So you don't even have to do anything. It'll just say automatically, if this is the scenario that you have, then y equals 0 is the horizontal asymptote. Because 5 is the bigger one. Okay. All right, next one, example number 6. Find the horizontal asymptotes. So we're going to start by figuring out what's the degree of the numerator, which is just the highest exponent of x, which in our case is 2. And then identify the degree of the denominator, which in our case is also 2. So these degrees are equal. They both are 2. So according to our reference chart, when the degrees are equal, that's the first scenario, then that just means that the horizontal asymptote will be the ratio of the leading coefficients. So I know that my horizontal asymptote will be y equals, because every horizontal line is just y equals, the ratio of the leading coefficients. Those are the numbers in front of the degrees. So 2 over 3 would be our horizontal asymptote. And that can't be simplified, so I'll just leave it as is. Example number 7, same thing, find the horizontal asymptotes. So start by figuring out what is the degree of the numerator, which is the highest exponent on the numerator, which is x to the 5th power. Then identify the degree of the denominator, which is the highest exponent of x on the denominator, which is 3. Now in our case, the numerator, which is 5, has a bigger degree than the denominator, which is 3. So the numerator is bigger in this case. So if we look at our reference chart, try to control this out. If you look at our reference chart, we're trying to figure out where it says the numerator is bigger. Degrees are equal, no. The degree of the denominator is bigger, no. Degree of the numerator is bigger by 1. It is bigger, but it's actually bigger by 2. And then the last case says the degree of the numerator is bigger by 2 or more. Bingo, that would be our scenario here. So in our case, the horizontal asymptote, it says there is no horizontal or even oblique asymptote. So for horizontal asymptote, I would just put none. And that would be our answer. All right. Okay, and then last example, number 8, find the horizontal or oblique asymptote, if any. So first step, anytime you want to find the horizontal asymptote, is start by identifying what the degree is of the numerator, which is the highest exponent on the numerator, which is 2. Then identify what's the degree of the denominator, which is the highest exponent of x on the denominator, which there's just x. There's no exponent clearly written on it. But when there's no exponent written on it, the exponent is 1. This is just x, but it's really x to the 1st power. We don't really write 1st power, but it is to the 1st power. Anything to the 1st power is itself. So in our case, the numerator has a bigger degree than the denominator. So if we look at our reference chart, the numerator is bigger, and it's bigger by 1, because this one's 2, this one's 1. So in this case, this would be our third scenario, which says there's going to be no horizontal asymptote. So I would write no horizontal asymptote. However, look at the second part. It says there will be an oblique or slant asymptote. Remember, that's the diagonal asymptote. Now, there is going to be an oblique or slant asymptote. I'll just go ahead and put oblique, but you can use the word slant. Now the question is, how do we find what the oblique asymptote is? Because it didn't actually say. Well, anytime you do have that third case where there happens to be no horizontal, but there is an oblique asymptote, the way you would find it is by actually dividing these two things by each other. You can use long division. For this one, you could even use synthetic division. So I would actually use synthetic division to find out what, I'm going to go ahead and use synthetic, to find out what the actual oblique asymptote is. But you could also use long division if you prefer that. And the way we do synthetic division is we start with this backwards L, and the number 4 goes into the backwards L. This is what we covered a couple classes ago. And on my top line, I'm going to start with all the coefficients of x. So starting with x squared, which is 3. Coefficient of x is -4, and then the constant is -7. And then we would just do the division. Start by bringing down the 3, and then multiply, add, multiply, add, multiply, add. So start with 3 times 4, that's 12. And then you add the two columns up. -4 plus 12 is 8. 8 times 4 is 32. And then you add -7 plus 32, and that's 25. That last number is always your remainder. So what this means is that my oblique asymptote will just be y equals, and it'll be 3x to the, well, our original problem was x squared, so our answer will be 1 less than that. So you can write x to first, or you can just write x plus 8 and that would be it. You don't need to include the remainder. The equation for the oblique asymptote is just 3x plus a, and then if there is a remainder, you would leave it off. And that's it.